So join SPS, make something like that. And really, as a physics major, it is, you know, I mean, I went to a college where it wasn't even optional. It's just like, if you weren't there, your professors were all over you. And that was actually a very good thing. Just so you know, I went to William Jewell, and then I went to WashU for grad school. But it's a good experience. It's an enriching experience. And in terms of looking at people who apply to graduate school, it's an expected experience. Not just that, but Sigma Pi Sigma, which is the honor society part of SPS that you can earn upon graduation.
And honestly,
Yes, I'm sorry, there was a question.
When do you guys have meetings?
So I'm gonna send an email to Professor Stoddard to send out to you guys. It's gonna have a doodle poll and a link to sign up on Root Groups. Signing up on Root Groups will make you part of the organization where you'll get all of our emails. And then the doodle poll, when you fill out the dates that you can attend every week, next week I'm gonna pick from the pool of whatever people put in where the most people can attend. So if you do want to come, make sure you fill out the doodle poll, and then next week I'll pick a date and most people can come. So it's not set yet.
Did you notice that some people are trying to join already?
Yeah, I've been accepting.
You're accepting them?
Yeah.
Okay, good. All right.
Yeah.
Okay.
and if you guys don't know a lot of people in the department, it is a great place to meet people. So at least hop in and introduce yourself once and get to know a few people. That's it. Thanks for your time.
All right. Thank you, Chris. Thank you, Gabby.
Yeah.
The other great thing that they do with their science outreach, with that volunteer work, that goes on your CV. That goes on your applications to graduate schools and things like that as well, that you care enough about science to try to keep it, you know, pass it on to underprivileged people. So, all right. You guys can keep packing, but I'm going to be dropping the screen right behind you, don't worry. All right, so let's go ahead and get started. I don't remember where we were before. All right, so today we've got a lot to do today. Wow. All right. So a lot of things to talk about today. I'm going to start, again, I am still following the book, although I'm going to start going a little bit faster. All right. So at least I'm going to try. It's so hard to talk fast. All right. So the next thing we had to talk about last time, well, because last time we left off on the topic of time, noting the classical approximation to time is that we all share a uniform variable of time for when an event occurs. All right. And so we're going to talk quickly about reference frames. All right. So the frame of reference, I'm going to assume that some of you guys have heard of that before. It is something relative to which you place your origin and your axes, and they are considered sort of at rest relative to that thing. A lot of times, what you will choose it relative to might be a boat or a fluid, like or the earth or whatever it is that you're saying. That's my frame of reference, and within it, this is my origin, and this is my x direction, and this is my y direction. That's my z. Whatever it is that you choose within that frame. Okay. Once you do choose a coordinate system, please remember that you should choose your axes in a way that makes the problem simplest. And a lot of times that will involve, like, maybe if you know the resulting acceleration of the particle, you would choose that to be one of your axes, something like that. I'll be modeling for you those good choices of frames of reference and coordinate systems throughout. So all frames moving at a constant velocity relative to each other are considered equivalent in classical, and we're going to talk about that a lot more in just a few minutes, so I'm not even going to bother to write that down. And inertial reference frames are those defined by Newton's first, and they are simplest because in those we can apply Newton's second. All right, that's all I'm going to say about reference frames, so I'm going to go ahead and move on. Masson Force. All right. We probably know that mass is a physical quantity that provides us a means of quantifying how much inertia something has. So I'll say it is a measure of inertia. And inertia, Latin for sluggishness, is the resistance of an object to being accelerated. In this context, that's what it means. All right. And, you know, there's a lot of ways to measure inertia, and I'm not going to go too much into it. Your book describes an inertial balance in a different way than I've ever heard of one, but it's interesting. The idea that you would go out to some area of microgravity and pull along some bar, and at the ends of the bar you might have mass 1 and mass 2. If the inertia of mass 1 is greater, the bar will rotate such that mass 1 lags behind and mass 2 is more easily accelerated. So in that case, you would get a general rotation about like that direction. You would have to operate that in a region of basic microgravity or with high accelerations, but you could also use GR to notice that we are in an accelerating reference frame and use the fact that the floor is actually accelerating up. And then all that you have is a scale, which is fine, a balance. But usually an inertial, just for your knowledge, usually, oh, I guess I should point this out. So we will pool this in a microgravity environment. And the thing with more mass will be less prone to acceleration and will therefore lag behind the other. Another thing, though, that is generally called an inertial balance, so this is described in your book as an inertial balance. But usually in practice, an inertial balance is something a little different from that. It's like some sort of a solid metal bar, and you would put your mass somehow connected, sometimes just set it on the end. But let's say that you connect your mass to the end of the bar. And then you would, you know, slightly deform the bar downwards, and so you're deflecting it from the equilibrium position, and then you're releasing it. And as a result, it will oscillate with an angular frequency that is proportional to 1 over the square root of inertia. So once you do that for some fixed object, you can use that as a unit and find it for other objects and compare. All right. You could also note, this is, again, I don't want to get too bogged down in these details, that mass, inertial mass, is actually proportional to weight. So if you want to compare two masses, you could weigh both of them at the exact same location, because even a mountain nearby can affect weight. And then compare those will each be proportional to mass. Okay. The 1 kilogram object currently is a piece of platinum and iridium in Paris, but we're changing that to silicon because obviously iridium decays, so that was not a good choice. Anyway, all right, so we have defined 1 kilogram as our unit of mass, and it is a standard object by which everything else is compared. All right, so are there any questions about mass at this time? Good. Let's talk about force. Force is a push or a pull. Okay? And, you know, you probably remember from your undergrad calc-based introductory course that one of the most difficult things about dealing with a system, if you're trying to analyze the forces on it, are figure out what the forces are and which direction they're acting. So, and your author here does a good job, probably a better job than your undergrad author did, at helping you with that. So, you know, so we will just notice that sometimes it is a challenge, and it will continue to be a challenge to know what forces are acting on an object. And in the case that, and right now we're going to continue thinking about point particles, but later on we'll also have to think about where those forces are acting when we have extended objects too. So I think that this is pretty well outlined by your author to notice a couple of things. First is, what is the object touching? Because in that case we can have contact forces. Normal force, tension force, friction force, all those things that involve touching are contact forces. And next, we will think about what objects are somewhat nearby. That can provide action at a distance forces. Okay? And those examples of those, well, I could have written my examples here, by the way. We've got tension forces, normal forces, friction forces, etc. For these, we will have gravitational force, electrical force, magnetic force. Those are the ones that we're going to be dealing with in this course for the most part. Okay. So that's kind of a nice thing to keep in mind, that you have to analyze the forces. The reason for that is as we apply Newton's second law, the whole point of Newton's second law will be to find the motion of something. To find the motion means to find the location as a function of time. Once you have that, it's very easy to find velocity, acceleration, and other things. But you can only do that if you understand the forces that are acting as functions of location and time. All right, so that's going to be something that we are going to consider as implicitly known, except that you actually do have to figure it out. But, okay. In terms of units of force, I guess I should have said up here, the unit here was the kilogram. The unit here unit will be the Newton, which is the force that's required to accelerate 1 kilogram at a rate of 1 meter per second per second. All right. In terms of measuring force, your author discusses a calibrated spring scale, meaning that you have this sort of scale here. You place your mass on the scale, and the spring stretches by some amount of deformation, which we'll call delta x. And by Hooke's law, we know that the force is proportional to delta x. So once we calibrate a spring scale, we can just mark on there what the different displacements correspond to in terms of the magnitude of the force. What is actually more commonly used is the piezoelectric. So you have maybe a solid disk. It's supposed to be a solid disk. And it's a novel material that when it's squished generates a voltage that's proportional to the amount of squishing. So and we still have deformations proportional to force. So if I go ahead and apply a force to that, then that deformation will be proportional to the force. This is supposed to look like a mass sitting on top. And that voltage will be proportional to the deformation. And again, we can calibrate it. We've got a scale. That'll be what you use most of the time in your life, I would think. All right. I know that last lecture was very boring, so I'm trying to get through the boring stuff because we got cool stuff too. All right. So also forces have direction because they are vectors, and the direction would be the direction the object would accelerate if only that force acted. All right, let's move on. Newton's first and second laws and inertial frames. So that is shorthanded. It says Newton's first and second laws and inertial frames of reference. Okay. I'm just going to have to move that page. I apologize. All right. Okay. are going to now actually begin thinking about analyzing motion. We're getting closer. And in the beginning, we are going to be analyzing motion of point particles or point masses. Point mass will be called a particle. It is a theoretical object with zero size, as it is indeed a point. So as a result, it can have no rotational motion, no deformational motion, only translational motion. All right. It is actually a good approximation for rockets and rocks and things like that as well. So it's worth learning about. All right. So let's begin with Newton's first law. Again, I know that some of you guys have had me for 240, 250, and I often complain when books get Newton's first wrong, and this book does it too. So I will correct it. The statement of Newton's first from your book is roughly, in the absence of forces, an object moves with a constant velocity. That is actually not Newton's first. Newton's first states, in the absence of forces, an object moves with constant velocity when viewed from an inertial frame of reference. And that defines inertial frame of references, and within those frames of reference, Newton's second will hold. All right? So let's go ahead and write that out. It is important. So in the absence of forces, an object moves with a constant velocity when viewed from an inertial frame of reference. And that's it. So this here says, in the absence of forces, an object moves with, so I'm always going to use with, a W with a slash to shorthand with, a constant velocity when viewed from an inertial frame of reference. All right. And that's what it should say. This law is sometimes called the law of inertia. It is also, could be called the definition of the inertial frame of reference. Okay. So because we are going to be happy to be able to apply Newton's second, and that's part of what we want to learn during Newtonian mechanics, we're going to choose to use inertial frames of reference a lot, all the way up till chapter 9, where you'll learn how to deal with non-inertial frames of reference. Okay. Another statement of Newton's first could also just be there exist inertial frames of reference, as long as the inertial frame of reference is defined that way. All right, so let's move on to Newton's second law. All right, Newton's second law states, for a particle with mass m, the net force on the particle equals that mass times the particle's resulting acceleration, such that F equals ma. I'll write it out. You only have to do that once. So for a particle with mass m, so far it says for a particle with mass m, the net force on the particle is equal to m times the particle's resulting acceleration, such that it can be written as F equals ma. All right. That gets boxed as well. This is also the defining equation for, it can be considered the defining equation actually for mass in terms of how mass is measured. All right. So I think that you guys probably remember that the original statement isn't quite like this, but we do want to start with this statement first in classical mechanics. All right, things to remember about this. We want to use our math to find location as a function of time. So what that means is that A will generally be written as time rate of change of velocity. Let's keep going. Time rate of change of velocity, which is the time rate of change of location. So A will generally be written as the second derivative of location with respect to time squared. And the reason for that is because once we put that into Newton's second law, all of a sudden, if we know m and we know the net force, our only unknown in the equation is r as a function of time. Yes, it's a differential equation. It's not one that you're going to do algebra to get it all alone. It's one that you're going to have to do calculus to get r all alone on one side of an equal sign. And we'll be modeling that quite a lot in the next few lectures. All right. Now, what we are going to do, though, is we are going to represent time derivatives with a dot on top. So I could also rewrite that line of reasoning as A is the time derivative of velocity. Okay. And I'm going to skip by that one, which is equal to the second time derivative of location. 2 dots on top. All right? So that's going to be the way that is more often written. But if you're more comfortable, you can write it this way. Both of those are equivalent. All right. So let's recall that there's another statement of Newton's second, which is actually Newton's original statement. And maybe it's a coincidence that this original statement is actually more general and more correct than this one here that we're going to be using in classical mechanics. His original statement is that the net force, and by the way, you've probably noticed already that the author sometimes uses F to represent net force. I'll try to be as clear as I can when I'm doing that. So the net force on an object is equal to the time rate of change of the momentum of the object, where momentum is represented by the letter P. So we could also write that, remembering our new formalism, as P dot. Okay. In this case, so this is the original statement of Newton's second law. In this case, I have used, so where the P variable is equal to the object's mass times its velocity. And this is our defining statement for momentum. Okay. And so in that case, if I go ahead and plug into that expression the definition of momentum, then what I get is that the net force is equal to the time rate of change of mass times velocity. And I will assume that just by moving, an object's mass doesn't change with time, which is a false assumption in terms of special rel, but this is the assumption that we're making in classical. So m can come out front. It will remain constant throughout the motion. And I've got m times dv dt, also known as ma, also known as m r double dot. Okay, so that reverts to the form that we'll be using in classical mechanics. All right. But, I think that one of the things that is most fascinating about Newton is how right he was and how he had no reason to be so right. But this really holds. All right. That holds everywhere. And let's go ahead and move on. Differential equations. Just like vector calculus, differential equations is its own class, diff-EQ, right? And I assume that you haven't had it, is what my assumption will be.
I'm in it with Rulov right now.
You're in it? Is anybody else in it at the moment? So we are going to be teaching that at the same time as the mechanics. So don't worry. I'm not assuming that you've had DiffEq. I'm not assuming that you've had vector calculus. All of this will be presented in the course. All right. So an example from here. So I have F equals ma. I'm going to make my substitution for a, the second derivative of location. All right. And then I'm going to get my variable all alone on one side, the equal sign. All right. So, and I can write that one more way. I don't mind going sort of back and forth. Second derivative with respect to t squared. All right, so let's say I have some system with different forces acting. By the way, this, again, your book is going to assume that you know that in the statement of Newton's second law, that is a net force, and just writes it as F. But just to be very clear, for a while, I'm going to write out net. So the net force of an object divided by its mass will be equal to the second derivative of location. And here, just mathematically, hopefully you see, I know mass. I'm going to assume that's given. I know net force. I know that's not that easy to find because it involves sums of vectors and things, but I can do that. And then all of a sudden, the only thing that's an unknown is this function here, whose second derivative is going to give me, is going to be equal to that function of location and time on the right-hand side of the equation. So how to figure out which function does that is what differential equations is all about. So I will be modeling that from the simplest. Hopefully I'll get past the simplest even today to something that is hopefully something new. So, all right. I guess we should be complete here. Let's go ahead and remind ourselves that if I have the, a one-dimensional mechanics problem, then what I do is I define the x-axis as the axis along which the motion is occurring. And so what I wind up with is fx is equal to max. I'm just writing it that way because that's probably what you're used to seeing, except that now we're going to note that this is the x component of the second derivative of location, which is the x component of location's second derivative, like that. Okay. And so in this case, let's say, we could actually go ahead and solve it if we want to. Let's go ahead and solve it. So let's assume that we'll let this be a constant. So I've got x double dot, just getting it all alone on one side of the equal sign, is equal to this x component of a force. And I'll go ahead and let that be sort of a constant. So I'm talking about a situation here where I have an object. It's confined to the x-axis for its motion because it's a one-dimensional problem. It has a force acting on it that is in this direction, and it has a constant value. We can call that F naught. All right, so the way to solve this equation for x as a function of time is to do the following. We're going to go ahead and do the way where we integrate both sides. All right, so I am going to take the integral with respect to time from time equals 0, which is sort of an arbitrary choice, to some time t on both sides. So you see I've done the same thing on both sides of the equal sign, and my equal sign will continue to hold. Great. So when I take the integral of the second derivative with respect to time squared, what I get, maybe I'm going too fast for you, but I'll just point out that this argument here is d2x dt squared integrated over dt. Now, in terms of the indefinite integral that results for that argument, what I will get is dx dt. So I get a value of dx dt. I could also write that as x dot if I want to. Whatever you're more comfortable with. And I have to evaluate that from t equals 0 to some later time t. So that's what I've gotten on the left-hand side of my equal sign. On the right-hand side of my equal sign, I have a constant that can come out front, f naught over m, times the derivative of dt from 0 to t, which gives me t evaluated from 0 to t. The integral of dt is t, the indefinite integral, and then we just have to evaluate it for its limits. All right, so what I get when I now evaluate my limits is I'll get x dot at value, at whatever value of t, where t will be now a function, minus x dot's initial value when t is equal to 0, and we'll use a subscript 0 to represent that. So that's x dot naught, also known as v naught. That's the initial value of the x component of velocity. Are we okay with that? Am I going too fast right now? Is it? Okay. All right. So, and then on the right-hand side, I've got f naught over m times t minus 0, which is just t. All right, well, that's fine, but I didn't want x dot. I did get x dot, so x dot as a function of time is equal to x dot naught. I don't know, does your author use v naught for that or x dot naught? Let me check. I uses v naught. So I'm going to get my next thing that has the thing that I want to solve for in it, which is this first derivative of location, all alone. So I'm going to add x dot naught, also known as v naught, to both sides. And I've got this expression. Again, that's great. That's velocity as a function of time. X component of velocity as a function of time. It's not what I wanted. I want location as a function of time. That is what motion is. So what I need to do is I need to, again, integrate both sides from 0 to t with respect to time. And I'll go ahead and write x dot as dx dt. All right. Okay. Now, the derivative, the integral with respect to time, oh, this should say dt, sorry. The integral with respect to time of dx dt is x, all right? I feel like some of this is so long ago from the beginning of calculus that I'm not sure that I trust that we all remember it, so I'm just going to say, let's just notice that integral is equal to x. And I have to evaluate from its initial to the final limit. And what I have here is v naught is, I'm going to go ahead and treat this as two terms. So I've got v naught times dt, the integral of which is v naught t, evaluated from 0 to t, plus f naught over m t squared over 2, evaluated from 0 to t. And some of you guys might look at this line and say, that's not the way my math professor would have me do it. He would have me, or she, of course. All right. I apologize. More likely she than he. All right. Anyway, would probably allow me to even cancel these. I don't know. Would they allow you to cancel your dt's and change your variable to dx so that you have to integrate from 0 to x, from x at 0 to x at t? I don't know what form they do that in. Do you know what I'm talking about? Do you guys know what I'm talking about?
Doing.
Yeah, I know, right? I'm trying to remember what the ticky-tack thing that your math professor would want me to do.
Like, what you're doing makes sense.
Okay, cool. Then I'm going to keep going.
They have us do something that doesn't make sense.
All right, then let's keep, but you're okay with this, the way it's written?
Yeah, let's not confuse ourselves.
Do I have to change this from x at 0 to x at t, or are we okay?
No, we're fine.
Okay, all right. So what I'm going to get is x's value at time t minus x's value at time 0, which I'm going to write as a subscript naught. And that is equal to v naught times t minus 0, also known as v naught t, plus f naught over m. Oh, how about if I go f naught over, I could put my, I'm going to put my 1/2 out front, sorry. 1/2 f naught over m times t squared minus 0 squared, so that's t squared. So my expression for my motion is x as a function of time is x naught plus v naught t plus 1/2 f naught over m t squared. And I look at that and I say, yes, that is correct. Because I remember in 240, I was rather limited to constant force problems, and in the one-dimensional case, there was, motion was described by a kinematic equation, which was delta x equals v naught t plus 1/2 at squared, where I noticed from Newton's second law that a is f over m for the system, right? So yes, we got it right. So this would be, but in terms of the method of how we start from Newton's second law, rearrange it so that our second derivative of location is alone on one side, the equal sign, and then just start integrating both sides with respect to time once and then twice, and what we'll have at the end of that is what's called the motion. The location is a function of time from here to forever, where that particle is going to be. And if you want to take its first derivative, you'll know its velocity is a function of time from here till forever, what that object's velocity will be. This is obviously the simplest case. We're going to do some more fun stuff. But this equation here is called the motion. If I ever ask you to find the motion of a particle, it means find location as a function of time. All right. And Newton's second law is often referred to as the equation of motion. It certainly is an equation of motion. All right. So again, I just want to reiterate that I will present all differential equations needed in this class. And it might not be that your math teacher would like it. Your math teacher might want this to say, oh, you're not evaluating x from those values. That's fine. I'm probably not going to pass muster in that way, but I have, me and my colleagues have done it all our lives, and we will certainly help you to do it like a physicist, if not to a mathematician's standards. Okay. So now we're going to talk about inertial frames. I do have a few things that are important and worth saying about them, but I will keep it quick. Inertial frames of reference. All right. So what I want to say about inertial frames of reference are, if Newton's first, that statement of Newton's first, holds, I'm trying to also interact with how your author writes it. Your author writes the statement, if Newton's first holds, then the frame of reference that you're using is inertial. So I'll use the statement that your author uses, but just be aware that we have slight differences in the way that we say things. So your author would say, if Newton's first holds, when viewed in the frame of reference S prime, then S prime is called an inertial frame of reference, and subsequently Newton's second will also hold. All right? Okay. Another thing to bear in mind is if Newton's first does not hold in a frame of reference. So let's say if Newton's second does not hold an inertial frame of reference, which we'll call S double prime. Then S double prime is non-inertial, and again, we'll learn how to deal with that in Chapter 9. But Newton's second will not hold in the form that you have learned it so far. You kidding me? Time goes too fast in this class. So the form of Newton's second, what we'd have to use for Newton's second, we'll have to wait until we're in Chapter 9 to learn. All right? Okay. Let's say that we have a third frame of reference, S triple prime, and it is moving at a constant velocity relative to S prime. Then it will also be an inertial frame of reference. So we'll say it too is inertial. So, let's go ahead and point out also that there is some issue about whether Newton's third would hold. And your author, again, has a really sort of well-defined picture of Newton's third, and works really well with that. But I will also say that as long as you're in an inertial reference frame, every time there is a force, it will obviously be of one of the four fundamental types, and it will be on a thing, by a thing, and of one of those, one of those four types. In a case that you're in a non-inertial reference frame, that no longer will be the case, would be the way that I would say it, in which case Newton's third, we don't have forces that always come in force pairs because we're not on a thing by a thing. But your author has a slightly different take on that that's actually, it hangs together pretty well with the rest of the book. So just know there are a couple different ways to state that. All right. Let's say, to illustrate that point, your author refers to ice cube in a train in a cup, and if the train's accelerating forward, the ice cube moves backward even though there's no net force on it. That's fine. It's accelerating backwards. There's no net force. Therefore, Newton's second didn't hold. Right? You guys agree with that? All right. There's also another point of view, which you could say, let's say that you're the person in a car that's veering left and you're in the passenger seat. Then, as that car veers left, you will accelerate to the right, within the frame of reference of the car, even though there's no net force on your torso causing that to happen. So again, Newton's second doesn't hold, but as soon as you're in contact with the door, right, you'll suddenly be at rest, even though there is a net force on you. So again, Newton's second doesn't hold. But you might think, sometimes we say that when that's happening, there might be this outward centrifugal force on you. But because the centrifugal force isn't by a thing, on a thing, or of one of the four fundamental types, it's actually not a real force. And therefore, it doesn't have a force pair force that goes with it because it's not by a thing. So also, conversely, if you want to look at it in terms of making up fictitious forces, that's fine, except now Newton's third would be the thing that doesn't hold. Is that okay? All right. Okay, so let's go ahead and talk about, I got a really cool problem I wanted to do with you guys. All right, I'm going to present a problem that you guys can think about over the weekend because I think it's going to be fun. I think we're ready. I don't think we have to talk about any more boring stuff. Even though your author, what does your author want to do next? Conservation momentum? No way. We're doing this. And then we'll come back to conservation momentum. All right, so let me zoom in because we're going to do a cool problem. Your author keeps trying to make it so boring. I like this book, but it puts a lot in the intro before you get to anything fun. All right, so the statement of the question is, David and Goliath are pushing a frictionless automobile of mass m, which is initially at rest. Goliath is strong but out of shape. Applies a forward push of magnitude f as a function of time is f naught, e to the minus time over tau, where tau and f naught are constants. All right, David, weaker but with more endurance, applies a backward push of magnitude force as a function of time, which is 1/2 f naught times e to the minus t over twice the time constant, so that he's not dying off as quickly in terms of his exponential force as magnitude. All right? What we're going to do next time at the start is we're going to calculate what's the net displacement of these two in this kind of like a tug of war, but it's a push of war at the end of time when it's all said and done. All right? So that's what we're going to do next time. And you guys can think about setting up that problem and solving the equation of motion if you would like. And that would be great. But if not, we'll go ahead and pick it up next time. Are there any questions for me right now? Have a good weekend. I'll leave that up till you're done writing.
When did you go to William Jewell?
Oh, from 90 to 93.
Because I worked at a cafe in Liberty, and I used to wait on this guy. I know him as Professor Pat, who was a physics professor there.
Oh, yeah.
So.
He actually, can you remember his last name? Because I should know it. I know him. Blaine Baker is one that I know really well because we went to graduate school and he wound up there. We went to graduate school together. But no, I love William Joel. Have you met Don Gilker? Do you know Don Gilker? Dr. Gilker?
I was engaged to someone who went there, but I wasn't going there myself because they weren't giving me any financial aid, and I don't have
It's
that kind of
expensive.
money.
I was a faculty brat there.
Oh, really?
Yeah. Yes, sir.
Huh?
Huh? Your homework assignment. That is a good point because I was going to assign it Monday, and I'm not going to scold you guys, but I am going to tell you what it is, and it'll still be that I officially assign it Monday. So there you go. Thank you for asking. You saved everybody a little bit of trouble.
Sorry, guys.
No,
Be
seriously.
that guy.
I'm not going to assign it right now. I'm just going to give you the weekend to know the numbers. I'll assign it on Monday. 8, 10, 18, 30, and 37. 18, 30, and 37. And hopefully those meet my goal of kind of ramping up difficulty from very doable to step by step, getting a little bit more challenging.
8, 18.
Just trying to,
8, 10, 18, 30.
gosh, is this a bingo game in here? Are you guys trying to mess me up? No, I'm just joking. 8, 10, 18, 30, 37. You're very visual. It is there. 8, 10, 18, 30, 37. Okay. But it won't be made on Friday and it won't be due Friday, even though it says on there I was going to make it today. I'm making it Monday because I forgot to assign it during the hour.
Will it still be due on Friday?
No, it'll be due a week from Monday. It'll always be due a week after the official announcement. You'll have 2 weekends. Thank you very much. All right.
Oh, that's great. I work all week. I don't have any time during the week.
Oh my word, I don't know how you do it. Let me see, let me stop my
That's the
recording
only
before you
free time
talk.
I have.